Hey everyone, welcome back to the channel. I hope you guys are doing extremely well. So in this video, we're going to learn about bridges in a graph. Now, what is the definition of a bridge? Very simple. Pick up any edge, and if you remove it, the component gets broken into two or more components. For an example, let's remove this. So the moment you remove this, previously it was connected. Now, can you see this is a single standalone component and this is a single standalone component. So they got broken down into two separate components, right? Now, imagine I say, okay, if I remove this, they're again broken down into two separate components. So it's a bridge. Now, what if I say, let's remove this? If you remove this, it is not broken down into two or more components. It still stays as a single component. So that's not a bridge. Imagine I remove this, it's broken down. One here and one here. So, what is the definition of a bridge? Very simple. Any edge on whose removal the graph is broken down into two or more components, that is the definition of a bridge. Got it? Now, which algorithm will we use to find a bridge in a graph? It's very simple. We will be using some logic in the DFS algorithm. So the prerequisite is quite straightforward. You must be knowing the DFS algorithm. Just in case you do not know the DFS algorithm, I made a detailed video on this particular playlist. Scroll up, you'll find the video for DFS. Go back and watch it and come back. Okay. So the prerequisite is DFS algorithm. So we will be taking this particular graph and we know the bridges in this graph. One is this, the other one is this, and the other one is this. So the problem is stating print all the bridges. That is the problem. It states print all the bridges. That is the question. So 4 and 5 is a bridge. You can write it as 5 and 4. 5 and 6 is a bridge. Again, you can write it as 6 and 5. 10 and 8 is a bridge. You can write it as 8 and 10. So there are 3 bridges. I want you to print all the bridges in this particular graph. That is what the question states. To implement the algorithm to find the bridges in a graph, what we will do is we will take two separate arrays. One is the time of insertion, while the other one is the lowest time of insertion. Now, what does that mean? Do you remember DFS traversal? How does DFS traversal work? Maybe it starts from 1, goes to 2, goes to 3, then goes to 4. So, first occurrence, like first time of insertion is here, second time of insertion is here, third time of insertion is here, fourth time of insertion. So, while doing the DFS traversal, keep a track. When are you reaching a node? In which step are you reaching a node? So the step at which you reach the node, that is what we call as time of insertion. Got it? What is the lowest time of insertion? What it does is it finds the lowest of all. So if I'm standing here, it will look at all the adjacent nodes and take the lowest among them, but it will not consider the parent. Did not understand? No worries. I'll be doing a proper dry run. You'll understand this. But remember this line, apart from parent. Apart from parent. This is the key point over here. Okay. So let's start on with the algorithm. So with the algorithm, how we start is we will write time of insertion and the lowest time. So let's start with 1. So that's where we start. So market is visited in the DFS traversal. The time of insertion is the first step. So timer will be 1 and the lowest time will be 1. So the first is the time of insertion. The second is the lowest time. Since initially you do not have any adjacent nodes, let's assume the current time is your lowest. And then we'll check around adjacent and we'll figure it out. Next, it will go to 2. So market has visited and the time of insertion is 2 and the lowest time is 3. Next is 3, 3 by 3. Next is 4, 4 by 4. Next is 5, 5 by 5. Next is 6, 6 by 6. Please make sure your market has visited. Okay. Next is 7, 7 by 7. Next is 8, 8 by 8. Next is 9 by 9. Now here comes a critical case that you need to understand. So at 9, when you're doing a DFS traversal of 9, it has a time of insertion as 9 and the lowest time of 9, right? Can 9 go to anywhere? And if I ask you, what are the adjacent nodes of 9? It's 8, which is where it is coming in from. If you look at this, so it's the parent because 8 is calling the 9. So it's a parent. And if you remember, you do not consider parent. Will 9 go to 6? In DFS, we did not visit nodes which are visited. It will not go. It will not go. But remember, of all adjacent nodes, that is what low is. But low will say, okay, I will not go there, but I'll pick up your low. Your lowest is 6. I'll pick up. So I'll just pick up that and write it to myself. Perfect. Now remember, this 8 called 9. So as of now, can I say 9 has no more adjacent nodes to go? It doesn't have anything to go. So it will come back. It will come back. Let's come back. So it will come back. Now when it comes back, can I say for sure that the 9's DFS traversal is complete, done and dusted? It is. It is. So 9's time of insertion is 9 and the lowest time is 6. Now 8 will say, hey, you are one of my adjacent nodes. Hey 9, you are one of my adjacent nodes and you did complete your traversal. So I'll update my low. What is your low? 6. Better than me. So I'll update my low to 6. So that is the definition of low. It says, I will take off all adjacent nodes apart from parent. 8 did not look at its parent. It took it from its adjacent node. 6 it got, it took and updated the low. Done. Now, once you have updated, it states, hey, wait, you have done your job. Now, can 8 and 9 be a bridge? Can this be a bridge? Okay, can this be a bridge? How do I check it? How do I check it? This is where these two arrays will help. Now he says 9 has done his DFS traversal. Can 8, 9 be a bridge? So he removes that. Hypothetically, just remove that. 9 says, hey, you're removing. He'll ask 8, what's your time of insertion? He says, in order to reach me, it has to be the 8th step. It has to be the 8th step. 9 says, I have an adjacent guy who can reach at the 6th step. The 9 says, I have an adjacent guy who can reach at the 6th step. So even if you remove, I can still go to the 6th step, and the 6th step will take me to the 7th, and the 7th will take me to the 8th. So I can reach you. Now, if I can reach you, it's not a bridge, because the definition of a bridge is split it into two components. So if I'm split into two components, I can't reach you back. So if there's a path to reach you back, it did not get splitted into two components. It's not a bridge. So I am sure that it is not a bridge. Now, since I know 8 and 9 cannot be a bridge, so like hypothetically I removed it, so hypothetically I'll place it back. Quite simple. Nice. So 8 has done for 9, the DFS is done, it has taken its lowest value. Now time to move ahead. Now we move to 10. So can I say it was 9 at the last step was 9th step. So this will be at the 10th step. So I'll write 10, 10. 10, 10 written and mark it as visited. Next, 11, 11, mark it as visited. Next, 12, 12, mark it as visited. Now comes the point. Let's erase this and write the DFS of 12. So when I write DFS of 12, can it go somewhere? It says, I have an adjacent node 10, but it's already visited. So I cannot go there. It's already visited. Now, if it cannot go there, because it's already visited, so you came via some path, and that is the reason it is visited. So this is never a bridge for sure. Because if it's visited, you would have visited in the previous path. So it's definitely not a bridge. But what's our job? Low will say, wait, I know 12, it's your adjacent node. So why don't you pick its lowest time? He just picks it and makes it 10. Nice. Next, can I say that the DFS of 11 called 12, and now 12 says, I have done my job. I'm complete. So whenever it's complete, what is 11's job? 11 says, 12, you are done and dusted. Your time in and low in is ready. I'll just take your low because that's better than mine. So I'll take it. Once I've taken it, 11 says, can this be an hypothetical edge? It tries to remove it. So 11 can be reached at the 11th step. And 12 says, I have an adjacent who can be at the 10th step. So I'll just go to the 10th and then I'll reach you. If I can reach you, This cannot be a bridge. This cannot be a bridge. This is not a bridge. Okay, fine. So let's erase this. Now, 11 is done. Who called 11? Let's write. 10 called 11. Can I say? I can. Now, 11 is done, so it will go back. Now, when it goes back to 10, 10 says, okay, he's coming back. He's coming back. So, what's my first job? Low says, okay, this is an adjacent node who has done his DFS traversal. So, his low is ready. I will just pick up. But it's already 10. Here is also 10. So, there's no point of picking it up. Now, next question. Can this be a bridge? Because I'm coming back. The DFS is complete. So, I'll just check for this to be a bridge. So, if I try to remove this, 10 can be reached at the 10th step. And 11, if you remove this, 11 says, I still have an adjacent where I can reach you back. So, not possible. This is not a bridge. This is not a bridge. It's not a bridge again. So, can I say now that the 8 called 10 and now 10's DFS is completed. 10's DFS is completed. So, now it will go back. Now it will go back to 8. When it goes back to 8, what is 8's first job? 8 says, 10, you are my adjacent. You have done your job. What's your low? 10. My low is 6. So, there's no point in taking your low. Forget about it. Now, the next step 8 says is, okay, let's wait. Can we be an edge? Can we be a bridge? For that, 8 says, what is my step? My step is 8. 10 says, the lowest step that I can reach to via all my adjacent nodes is 10. So, I cannot reach 8 or something before 8. So, I cannot reach you back. If I cannot reach you back, I am stating that this guy is a bridge. I am stating that this guy is a bridge. Perfect. Done. So, we got our first bridge. Got our first bridge. Now, 8 says, I've done with 9, I'm done with 10, I'm done with all the adjacent nodes. So, I'll now go back to 7. Now, when it goes to 7, so 7 ideally would have called 8, right? Now, 8's job is done, so it goes back to 7. 7's first step is low. So, I'll say, 8, you are done. What's your lowest? 6. So, I'll just pick you. I'll just pick. He picks up. Now, next step, 7 and 8 check for bridge. So, when they check for bridge, 8 says, okay, my lowest is 6. I can still go to 6. 7 says, my step is 7. So, if 8 can reach 6, that means it can reach back 7. So, this is not a bridge. This is definitely not a bridge. So, 7's DFS is done. It will now go back to 6. So, let's write for 6 now. Wait. So, I'll be right. DFS of 6 called 7 and 7 is done. Right? What's 6 first job? Low. Low will be looking for it. Low says, okay, 7, you're done. What's your low? 6. My low is 6. No need to do. No need to do anything. So if I remove this, 7 says, I can still reach back 6, which is your step, which is via this. Because that's why it is 6 and this is 6. So even if you remove this, I can still reach you back. No point. No point. Not a bridge. Done. Can I say 6 is done? I can say 6 is now done. Who was called by 6? 5 called 6. So it goes back. The moment it goes back, 5 says, wait, you're my adjacent. Low is again looking for it. 6. It has 5. It will not take it. 5 says, my time of insertion is 5. 6 says, the lowest I can get is 6. I cannot reach you back. 5 and 6 is a bridge. So I got one more bridge. Perfect. 5 is done. What's the next step? 5 says, let's go back to 4. 5 says, let's go back to 4. So 4 which called 5, the 5 will go back to it. The moment it goes back to 4, 4 slow looks for it and says, you have 5, but I have 4. I'll not. 4 says, hey, I need 4th step. 5 says, the lowest I can get is 5th. So 4, 5 is a bridge again. 4, 5 is a bridge again. So I can say 5 is done and we have figured out 4, 5 is a bridge. And do you remember how the DFS call happened? 1 came here, then it went here. But 4 did not check out its other adjacent node, which was 1. So now it came back. Now 4 will try to go here, but it's already visited. So it will not go. But since it came via here, it can pick up the low and update him because he's greedy. So just look for the adjacent node slow. They'll update him. Now 4 will try to go back to 3 because that is where it came from. The moment it tries to go back to 3, 3 is greedy. 3's low is greedy. 3 will look for, okay, wait, let me take your low. So I'll take it slow. That's the first thing you'll do. Next, I'll try to see if 4 and 3 can be a bridge. 4 and 3 can be a bridge. So 4 says, okay, I can reach the first step. 3's entry time is 3. So I can reach this, not a bridge. Similarly, you can track back and do everything. So apparently we got 3 bridges. One here, one here. That's how easy it was. So I hope you've got the intuition. The intuition is pretty simple. Pretty simple. The reason we have stored low apart from the parent is very simple. Like if I just draw it, this is the parent, and this, like, the parent is usually the node, and this is the IT. Now the reason this IT guy is not storing the low here is because we are removing this. So if there is someone else who can take before the parent or to the parent, that is what we need to look for. That is why we are not storing the parent's low. Got it? That's a simple intuition. I just look for if there is any other way I can go back to prior to that DFS traversal or to that node. That is the simple intuition behind this, like, small. I hope you've understood the entire intuition and the algorithm. Now it's time to code it up. So the problem is critical connections in a network. It states the graph is zero based indexing and so and so. You have to find all the critical connections. So the definition of bridge is defined as critical connections over here. What are we given? N and the connections. So they're basically given the edges. So you have to form the graph yourself. So as usual, I'll be coding the C++ solution, and you can figure out the exact similar Java code on the left. Okay. So let's quickly start coding this up. The first step is pretty simple. We'll create the adjacency list of size n. Let's go across the connections, which is this. And what we'll do is we'll say adjacency of IT of 0, because this is a vector. So push back of IT of 1. And you can just copy paste the same line because it's an undirected graph. And you can say IT of 1. So off with ID of 0. So the graph is created. Once the graph is created, what do you require for the DFS traversal? Just think yourself. You'll be requiring a visited array. So let's go across and mark it. You'll be requiring a TN. You can mark everything as 0. And you'll be requiring in this. What's the other thing that you'll be requiring? You'll be requiring to store all the bridges. So maybe we can create a vector of int, and maybe you can call this as bridges. That is what you want to store. And we require a timer, so maybe we can declare it globally. Timer equal to 0. That is the step, or you can keep it as 1 as well. Now let's write this as void DFS int node. Okay, we need the parent and we need the visited, and then we need the graph as well. So go ahead and take the graph. That's the adjacency list. What else we require? We require the time in, and we require the lower time. Done. Now, the moment you enter the graph, what's the first thing that you will do? The first thing that you do is mark it as visited. So go across and mark it as visited. What's the next thing that you'll do? You will say time of insertion of the node, and the lowest time of the node is equal to timer, and then you can just increase the timer for the next step. Now go across and travel for its adjacent node. Now something I know is if the adjacent node is the parent, we don't need to call the DFS, or we don't need to take it into consideration. So if the adjacent node is equal to parent, let's not do anything and go ahead. And the other thing can be if it's not visited, right? Or else if it's visited. That's two of the cases. So remember, if it's not visited, what's the first thing that you'll do? We will go and traverse for it. So IT, the parent will be node, the visited, the adjacent, the TN, and the low. Once the DFS of IT is completed, it comes back. Node is greedy. So node says, you have came back, right? Okay, wait. What's your lowest time? Give it to me. And he takes it. I've taken the lowest time. Now he's taken it. Now he'll say, okay, can this node to IT be a bridge? He'll ask. So for that, he'll say, hey, adjacent node, what's your lowest time? What's your lowest time? This is, so adjacent node will say, my lowest time is low of IT. If that's somewhere lesser than equal to the current node's time of insertion, then he can reach. But if it is not, if the lowest time is greater than the time of insertion, then he cannot reach the current node. That means it's a bridge. So you go across and say it is a bridge. And maybe you can just store this. It is a vector of vector, int, and bridges. Perfect. So you can just take this bridges. Perfect. And over here you can say, okay, this is a bridge. So bridges dot push back, because if we cannot reach, because if the lowest time cannot reach before or equivalent to the node, that means they got split into two different components. I can write as IT and node. This is a bridge. You can write it as node and IT as well. Perfect. Done. What if it's visited? That means while the DFS traversal was being done previously, you would have visited it. So you have already visited it. So it's definitely in the same component, even if you remove that. So bridge, not possible because you're coming via visiting it. You're coming via visiting it. So how can it be a bridge? I'll just be considered with the lowest time. So he is just bothered about himself. He'll be like, hey, adjacent, I don't care. Just give me your lowest time. I'll just take it. It cannot be a bridge, I know. So it's perfect. This is how you can write it. Just take the lowest time of the adjacent, compare it if it can reach. And once you've done this, call the defs. By the way, assuming it's a single component, we start from 0. We give the parent as initially as -1. We need the visited, we need the adjacent, we need the time of insertion, we need the low. Okay. Make sure you pass everything correctly, otherwise it will be a mess. And once you've done this, you can return the bridges. So this is how you can easily get all the bridges. Now let's quickly go and run this and see if it is running fine. Okay, we have some mistake. Let's see what mistake we have. Okay, there is a breeze missing. Okay, we've given that. Now let's quickly run this and see if it is running fine. It is. Now let's submit this and see if it is getting submitted or not. So now it's time to discuss the time complexity and the space complexity. First, let's discuss the space complexity. We're using like 3n over here and v plus 2e to create the graph. So v plus 2e and then 3n. So you can say plus of, that's the space. Yes, that's the space complexity. What is the time complexity? Can I say I'm doing a DFS traversal? And you know the DFS traversal takes v plus 2e. So this time complexity is v plus 2e. So this is how you can easily find all the bridges in a graph. So I hope you've understood everything. Before wrapping up this video, I have a very quick request to make. I was going through our channel statistics. Nearly 50% of the users who watch our video do not hit that subscribe button. So if you're new to our channel, please do consider subscribing to us. If you've understood the intuition, the algorithm, and the code, make sure you hit that like button. And if you haven't checked out our SD sheet and the other playlist, all the links will be in the description. Make sure you check them out as well. With this, I'll be wrapping up this video. Let's meet in some other video. Till then, bye-bye team.
Whenever your heart is broken.